2, 3, and we're going live. Sure. And we're live. Great. Hello, everyone. Welcome to the second virtual edition of Astronomy on Tap, Cambridge. Today, we have another fantastic speaker, Dr. Nina Sartorio, who will tell us something about herself in a second. And to remind everyone who hasn't seen us before, let us quickly reintroduce ourselves. My name is Asha, and I'm a PhD student at Cambridge Institute of Cosmology, researching galaxy formation and evolution. Off to you, Johnny.
Hi, I'm Johnny. I'm a first-year PhD student in the Institute of Astronomy, and I study planetary atmospheres and interiors.
Off to you, Annabelle.
Hi, I'm Annabelle. I'm a first-year PhD student at Cambridge. I'm studying clusters of galaxies and the black holes at their center.
Thank you. And Haley.
Hi, I'm Haley. I'm a postdoc in the maths department at the University of Cambridge, and I work mainly in cosmology and general relativity.
Thanks. And finally, the star of today's show, Nina. Tell us something about yourself, please.
Hi, so I'm Nina Sartorio. I'm also a postdoc in the Institute of Astronomy. I have worked mostly in star formation in the past, but right now I switched to cosmology and I'm studying the very beginning of the universe.
Thanks a lot. That's fantastic. So, before we go on to Nina's talk, a couple of bookkeeping things. We'll start with the talk, followed by question and answer. And in order for you to engage in asking questions, please go ahead and join at the webpage slido.com, putting our hashtag event code capital A O capital T AoT. That's where you can ask questions and then join the quiz that we prepared for you called When Was It First Observed, or When Was It Discovered? So in order to join the fun and ask questions, please go to slido.com, hashtag AoT. I'll also share that information later during the talk. So on that note, let's leave the stage to Nina and listen to her wonderful talk.
Well, thank you everyone for coming. So I'll start by sharing the screen here. So today I'm going to be talking a little bit about X-ray binaries and their importance in the early universe. So I guess most of you are tired of hearing that the universe started with a Big Bang. So just after the Big Bang, we think the universe was really small and really hot. And because it was so hot, we couldn't see most of the particles that we see today. We had instead what we call a primordial soup, which was made mostly of quarks and gluons. We call it a quark-gluon plasma. And as the universe started expanding, it started to cool down a little bit, and in a fraction of a second, it was already able to form the very first protons and neutrons. So you can see protons and neutrons here on the left-hand side. So protons and neutrons are made of quarks. So these are the color balls here. And a proton is made of 2 up quarks and 1 down quark, and the neutron of 2 down quarks and 1 up quark. And what keeps them together are those other particles called gluons. And if you give it a little more time, just about a minute, the universe was already the size of a tennis ball. And by then, we already could pair up different protons and neutrons to form the very first nuclei that we saw in the universe. But it took over 300,000 years actually for the very first atoms to form. That's because it was still too hot, and the electrons that are needed to form a full atom were still whizzing around the universe, and they couldn't bother to keep around the nuclei. So what is going to be really important is that at some point the universe becomes what we call neutral. That's when all the nuclei actually are able to capture a number of electrons that is equal to the number of protons in the nuclei. So here you can see is a neutral helium atom. So you have 2 electrons and 2 protons in the nucleus, so the positive particles here. Now something really amazing happened at this point, because when the universe became neutral, light was suddenly free to travel. Before that, when you had ions and electrons just traveling around, just scattered through the universe, light couldn't just go and travel as much as it wanted. It always wanted to interact either with these electrons or with the ions. And what happened is that the ball was a little, the light was a bit like a ball in a pinball game. It kept scattering and jutting about, and it couldn't just travel long distances. When the universe became neutral, suddenly the universe became also transparent. So it went from being foggy to being completely clear. And at that point is when we got emission of light, which today we see as the cosmic microwave background. So this is what we see here. So here on the right hand corner is the Planck satellite that took this beautiful image. And this is a type of light that you can see through the whole of the night sky. So it doesn't matter where you point your telescope, you're always going to see this cosmic microwave background. It's called microwave background because it is in the microwave wavelength of light. It wasn't always microwave. Back the day when it was emitted, when the universe became neutral, it was actually invisible light. It looked a bit orange. But as the universe expanded, the full wavelength of light also got stretched to the point that now it went all the way from being an orange light to being a light in the microwave size. So if you see here, it looks like it's, if you look at different points in the universe in the night sky, the cosmic microwave background looks very different. That's actually not true. So if you saw the brightest red dot here and the deepest blue dot here, they are actually less than 1% different from each other. And these differences that you see are very, very minuscule, but they are also very important because it is because of these differences that some bits of the universe manage to cool slightly more than others and accumulate slightly more mass than other bits of the universe. And these bits of the universe that had more mass were the bits of the universe that started forming the very first stars and the very first galaxies. Um, so, as you might have heard, most of the universe is actually, the matter of the universe is not actually the matter that we see in everyday light. It is actually dark matter. So, this is a type of matter that does have gravity, but doesn't really interact with light. It doesn't really interact with electromagnetic waves. So it is in those different regions, the cooler regions, that you start to form a big clumps of dark matter with what we call dark matter halos. And these dark matter halos, as they clump up, they exert a lot of gravity and they start attracting gas towards the center of this halo. So this is sort of what you can see here. So this is what we call the cosmic web, and this is a little bit what I think the universe looks even nowadays. So you can see these filaments and you can see these hubs, and these hubs is where you have this dark matter big halos that are attracting gas through these filaments into the halo, and as the gas falls, it collides with itself and it starts forming the very, very first stars in the universe. So it is important that we understand how all of this started to work, how this very first mini halos formed, and how material fell onto them to form the very first stars. Now, what just doing a quick recap. So basically, if you see here on the left hand side, what you have is the Big Bang. The universe became neutral. You emitted the CMB, and then the universe was dark. It didn't have anything emitting light. So this is what we call the dark ages. And at some point, once enough gas had fallen into these halos, you started forming the very, very first stars in the universe and the very, very first galaxies. And these galaxies and stars started emitting the first light. So that's what we call the cosmic dawn. Now, the interesting thing is that those stars, they emit light at another frequency, that's the UV, the same one that if you go to the beach is going to burn your skin. Well, basically they also did damage to the early universe as well. So what they started doing is they started screwing up those neutral atoms and they started making them ionized again. So they started creating these bubbles around every single primordial, let's say, galaxy with lots of stars, and they started making the universe ionized. And actually, these bubbles started growing and growing, and today, the whole space in between galaxies is completely ionized again. And this is really cool because if the space wasn't ionized, if it was completely neutral, then we wouldn't be able to see the light from other galaxies because they would just be stopped halfway by this neutral gas. But because it's completely ionized, light can just travel and reach our eyes, and we can actually observe different galaxies and different stars and see all the cool astronomy that we do today. So basically what we have is what we call the Swiss cheese model. So each one of the stars start making this bubble of ionized gas around them, and it looks very much like a Swiss cheese. And these bubbles start growing and growing and growing until the whole universe is ionized. That's also what I have here on this video on the left. I'm going to play it again. So everything that's in red is the neutral gas, and every single one of these green points is a full galaxy. And as these galaxies appear, they start making the universe transparent to light, as you can see here. So you can see it start making these little bubbles everywhere, and they start growing and growing as you get more and more and more galaxies, until eventually the whole universe gets ionized. Okay? Now, this is if you were to consider only this UV light, this ultraviolet light from stars. What we had the idea of doing is also studying what X-rays do. So X-rays, just like UV, are also able to ionize these atoms. So basically, you have here a neutral hydrogen, and if you have an X-ray coming in, this X-ray can actually kick off this electron from the hydrogen and make an ion. So basically, you're left with a proton and an electron traveling at very high speed. And this electron can then cause a lot of damage and do different things. It can create more ionize, so it can ionize even another hydrogen. It can excite the emission of some lines, some of their different types of light, and it can heat the gas. So basically, these X-rays, they are able to also ionize and also heat the environment around them. The difference from X-rays, from UV radiation, is that the X-rays don't contain themselves to the region around their mother stars or their mother galaxies. They actually can travel very far away, and they can start affecting this region in between in the cheese, kind of melting the cheese in between the bubbles here of our Swiss cheese model. So this is an image of Centaurus A. So this is an AGN, is an active galactic nuclei. So it's just a huge black hole that is accreting a lot of mass. And these are the main emitters of X-rays in today's universe. But we are actually caring about the universe much further back, when the very first stars were forming. And at that point, you didn't have this really supermassive black holes, because black holes take time to grow to that size. They actually have to either eat up a lot or merge with a lot of other black holes until they become a supermassive black hole. So actually, if you look back in time, so this is a little graph. So here, redshift can be thought in a way as analogous to being time. So the higher the redshift, the older it is. So this is a lot older. 0 is where we are right now. And the colored lines here are the AGN. And you can see that after some point, we can't find any AGN anymore. So something else must be emitting X-rays in the early universe. And we started to try to wonder what these things were. So the first things we did is to run simulations at the early universe, and we started to see that much like today, most of the stars don't like forming on their own. They form with other stars. They have companions. So they are born usually in pairs. So they are what we call binaries. So we started to wonder, can these binaries produce X-rays? And it turns out, yes, in some circumstances they can. So when does a binary emit X-rays? So you need to have what we call a compact object. So this is a black hole or a neutron star. So this is a star that has evolved through the whole of its lifetime. It has exploded in a supernova explosion, and you are left with a very compact, very dense object. So if you were to take, for example, a little teaspoon of a neutron star, it would be, tons and tons and tons. So you wouldn't be able to even lift it. And in addition to this compact object, you have a companion that still hasn't died. It hasn't gone supernova. It hasn't become black hole or neutron star. It could be a star, for example, like our own sun, right? So how do they produce X-rays? Well, what happens is that there is a little region here that each star has their gravitational field or their gravitational force dominating. So if you're inside this blue bit here around the compact object has a greater gravity than the other star. The same thing if you are in this region here, in this region, this star, the companion, dominates. Now what happens is that sometimes the compact object is able to steal material from its companion star. And this material starts falling into the gravitational field of the compact object. Because this compact object is very compact, it actually it has a very steep gravitational field. So as the gas from the giant star starts accreting, it accelerates and it heats up a lot. So it would be the equivalent of you going into a very, very steep slope and getting a lot of velocity, right? And then as a result, you heat up a lot. And because you heat up a lot, then you start emitting those X-rays. So that's where we think the X-rays from the very early universe came from. And what we started to do is then to run lots and lots and lots of models of all the stars from the early universe. So we ran thousands and thousands and thousands of binaries over this code that's called binaries. And I'm going to show you a little video now of what the code does in a way. So here we have two stars at the very beginning. So what's going to happen is now one star is going to evolve. It evolved to a red giant. It stays like this for a little bit, and now it's going to explode as a supernova. Boom. Okay, cool. So now we have our compact object there. So that's our neutron star in this case. And then the other star actually also evolved to a red giant. And as it evolved, it filled up that gap in which the neutron star dominated the gravity, and it started pulling on material. And then it creates this accretion disk, and as this gas accretes, it can actually start emitting X-rays. So what did we find from running lots and lots and lots of these models? So basically what I'm showing here in this graph, so here on the y-axis, you have the number of binaries, all the binaries that we had in a particular one of those halos of dark matter from the early universe. So this very primordial places, this places where primordial stars and primordial galaxies developed. And here on the x-axis, you have the mass that you have in stars for each one of those halos. So you can imagine how this is analogous to the amount of stars that you have in each one of those. So you can see that for the very early universe, so this is redshift 30. This is a few 100,000 years after the Big Bang. And what you can see is that you don't have many binaries, right? So you have maybe 6 binaries. And here the ones that have the red circle are the ones that actually have an X-ray binary. They don't not only have binaries, but they have managed to develop an X-ray binary. So you can see that maybe you have a few mini halos that have X-ray binaries, but most of them actually don't have any binaries at all. As you evolve in time, then you have more halos that start forming stars, and you have a lot more of them that manage to have at least one X-ray binary. And you can see here the number of binaries has increased a lot. And if you go to redshift 10, so this is more than 500 million years after the Big Bang, then you have really, really, really lots of halos, and you have more than 200 binaries in some of them. And here I didn't plot the red circles because literally every single primordial galaxy we had at this point actually had one of those X-ray binaries emitting X-rays. So what does that mean for the early universe? Well, what you can think is that, remember the Swiss cheese model that we had? So you have the Swiss cheese here, and on the top of the Swiss cheese, you have some regions of space that actually have a lot of binaries in the early universe, and some regions that actually don't have any. So what you have is a differential heating of different bits of the universe. So some bits of the universe can get ionized and heated up quite quickly, while others are gonna remain neutral and cold for a very, very long time. So that's what we are looking into now. And what is cool about this is that there is one type of radiation that we're starting to be able to observe today, which is called the 21 centimeter line. So the 21 centimeter line is basically a changing spin. So spin is a characteristic quantum property of the electron of an atom. So if you think of our neutral hydrogen that we saw before, when it changes this property from being spin up to being spin down, what happens is that it emits this line, which has a wavelength of 21 centimeters, so it's called the 21 centimeter line. And this emission, the probability of it happening, it's very, very linked to the temperature. So if you think about it, if you had some regions of space that were heated up by X-rays, then the emission of this line is gonna look slightly different from the detection of this line in the region of space where it's neutral and cold. So by observing this line, what we hope to do is to look at different bits of the universe and see how different it is, the different regions. How if you have regions that are very cold and regions that are very hot. And by doing that, we can try to link them to this X-ray binaries. And linking them to the X-ray binaries, we can start getting an idea of what type of stars existed in the very beginning of the universe. And then from that, start getting an insight on the formation of the very first stars. So that's what I had. So you can ask questions now. Thanks for watching.
Thank you very much, Nina. That was really great. Thanks a lot. So in order to hopefully I can smoothly change into the questions. Did I manage? Yes, I think I did. If you don't mind stopping sharing your screen for now. Great. Oh, yep. And we're back. So I will read off the questions to you, and if you don't mind, you will then answer them for us, if that's okay. Great.
Yeah, sure.
So, the first question we have on the list comes from someone called the Ragdoll Kitten Lover, and the question is: when the universe was made, how big it was?
So the universe came from what we think it is a singularity. So it's basically non-existent in size. So we don't know exactly so we know that the universe has started in something like the Big Bang, to the point that it was really, really small, and then now it's very big. But we don't know, for example, what banged the Big Bang, or what causes a Big Bang, and if there are more Big Bangs around. So those are still very open questions. But the idea is that the universe at some point was smaller than the size of an atom. I hope that answers your question.
Whoa, thank you. It's hard to imagine, isn't it? Right, we've got the next question from Bella, which is maybe not directly astronomy, but definitely on the topic, which is: could you see protons and neutrons from a microscope?
From a microscope. So what you are know, because for you to see something in the microscope, right? It has to sort of interact with light. So you're trying to see something that is around the same size as the wavelength of light as you see it from a microscope. So there's a limit in what you can see on a microscope, and it's usually around the size of an atom.
Thank you. I hope that answers Bella's question. If that's not understood, maybe she can follow up. They can follow up with another question. So we've got another question from Bella, actually, that was voted up, which is: how is proton different from a neutron? Is it anything different in the structure of both things?
So yes. So basically, what mainly distinguishes the proton and the neutron is that the neutron has, as the name says, it's neutral in electric charge. So if you had an electric field, a neutron wouldn't feel any force towards this electric field or away from this electric field, where a proton as it's positive. It has a positive charge. So and why they have that is because of those quarks that form the proton and the neutron. So if you have two ups and one down, then that's a proton. If you have two downs and one up, that's a neutron. So they change in one of those quarks, and this quark basically makes the whole difference between how the proton and how the neutron actually behave.
Thank you. So now, I think we're switching gears because the next question comes from the ragdoll kitten lover who already asked a question, but it's it's a nice one. Is there anything in a black hole?
That's a very, very hard question. So things get, absorbed sucked into the black hole, if you will. So there definitely is something there, right? Because things don't just disappear. It might be mostly energy, because you're accelerating things to very, very high speeds. And if you remember that very famous equation of Einstein, so E equals mc squared. So what that basically is saying is, if you take any mass and you accelerate it to the point that it has the speed of light squared, then to the speed of light, basically what you can do is you can transform it into energy. So in a black hole, that's virtually what's happening there. That's why not even light can escape from a black hole.
Awesome. I think we've got the next question voted up is also concerning black holes, but maybe in a different sense. Someone called I Love Astronomy asks, does a black hole have to be an AGN for astronomers to see it?
No. There are other ways that you can detect black holes. So one of the things is, for example, if you see for the X-ray binaries that we were discussing, if something mysteriously gets sucked into a blob of nothing, that's usually indication for the black hole might be there. The other thing is black holes have very strong magnetic fields. They have strong gravitational fields. So what happens is that light itself gets distorted from their path as they go past close to a black hole. So this is similar to things like gravitational lensing. You might have heard of this. So if you have, for example, a black hole here and some light coming this way, it's actually gonna go around the black hole like that. So sometimes if the light comes from an object, goes like this in one side and like this on the other side, you can actually see the same star twice, just by the lensing, by this distortion that the black hole creates on the light of objects that are behind it. So this is another way of you measuring black holes.
Thank you. We've got, for now, at least 2 more questions, if you don't mind, Nina. Sorry for keeping you so long. We've got another one from I Love Astronomy, which is, when the first star explodes, can it hurt the second star? I think it concerns the video rendering you've showed.
Yes, so when the first stars explode, so when it goes supernova, it releases a lot of energy. So the supernova are one of the strongest phenomena that we know in astronomy. For you to have an idea, when a star goes supernova, it can be brighter than an entire galaxy. And in 1054, when one of the supernova went off, it actually really close to us, actually. It was visible during daytime for over a week. So it's very amazing how much energy that is. So when it releases that much energy, if the other star is very close by, it can actually get kicked away, or it's like as if the supernova made the neutron star, well, what with the neutron star kind of have a little back jet, and it can fly away at very high speeds. Sometimes you find these neutron stars traveling at thousands of kilometers per hour, and it's because of what we call the supernova kick that it gets when it is in binary pair, and then it gets ejected somehow. So yeah, it can disturb the binary system, and then you can end up with 2 individual stars, basically.
Thanks. That's very interesting, actually. Thank you. We've got, so there was one more question added, so if you don't mind answering 2 more, that's okay.
Okay.
So the next one is from, I'm trying to pronounce it correctly, Suhail. Have there been any X-ray binaries observed in the Milky Way? If so,
Ye-
does it give any indication of the formation of the Milky Way? Sorry, it was a long one.
So yes, there have been X-ray binaries, lots of them actually, a few hundred detected in the Milky Way already. They do help you to trace something. So, for example, because so stars are a bit like dogs. So very big stars, they live fast and they die young. Whereas the small stars, they tend to live for a very, very long time. So stars like the sun live billions of years, whereas the stars that are like tens of times the mass of the sun usually just live a few 100,000. Um, so because those binaries, you need to have like a neutron star or a black hole. It means that you needed the star with a very high mass to begin with. So those stars, they live very short time. So if you see an X-ray binary, you can already know a little bit of the stars that were there at some point in the past. And that helps us trace which types of stars formed and how many massive stars formed in a certain region. That said, it's more helpful to use X-ray binaries to do this type of inference for other galaxies or regions that are very far away, because the Milky Way, we have so much information, much better information. We can actually see stars forming in the Milky Way. We can actually point our telescope to a cloud where stars are forming and actually observe it, in situ. So the interesting thing is actually using this detective work with X-ray binaries in other places where we don't have, as good data as we have for the Milky Way, basically.
Great. Well, thank you. That's a very exhaustive answer. I think the person asking it will really appreciate it. Thank you, Nina. Okay. All right. There are more questions coming in, but I think there is one which is on topic and one which is off topic, and that's where we draw the line. So
Okay.
the one on topic: does a black hole stop after some time? And if yes, then where do the things that it sucks go?
Um, so that's a very good question. It might be a bit above my understanding. So there are some black holes, and we know black holes can evaporate. So, for example, you might have heard, and lots of people went bonkers at some point because CERN can actually create these very, very tiny black holes that can actually evaporate. They last like milliseconds, and it's nothing to be concerned about. It's
Yeah.
not gonna swallow the Earth and anything. Bigger black holes, we do not know if they can actually disappear or not. So far, it looks like it might be a difficult thing. There is something that can maybe radiation that I'm not sure it's okay to call it coming out of the black hole, but for example, Hawking radiation is when you have two. So this is very complicated. So, for example, in quantum mechanics, you have what we call a background energy field. So you can create pairs of particles and antiparticles. So you can have things like a proton and an antiproton. And this antiproton, if you combine it with a proton, it disappears again, basically. Um, so what you could have is things like you create a proton-antiproton pair at the very edge of the black hole, and one gets sucked in and the other one doesn't. Then you can have this radiation out of the black hole. But if and theoretically, if you were able to, send enough antiprotons or anti stuff inside a black hole, then it could start disappearing. But there is no measurement as far as I'm aware of that happening. So it's still very theoretical. And certainly there are people that can answer this much better than I can, because it's really not my area of expertise.
Well, I think you've done a great job. So let's. I hope that's a satisfactory answer. So there's one last question, and I think you'll like it. What is your favorite star from Vegetables in Space? Sorry, Vegetables in Space is the name of the person asking.
Okay. Oh, my favorite star. That's very hard.
There are just way
I
too
don't
many
know.
stars.
I don't know. I think probably Raijo. So the one on Orion's knee. I always find it, very nice. It's a blue giant. It's very bright and easy. It was always the one that I went for. It and Betelgeuse are the ones I always go for when I'm trying to find Orion in the sky. So I think, yeah, probably that one.
Awesome. Yeah. So I guess homework for anyone interested in finding Nina's favorite star is to look up at the sky when the night is clear and actually find Rigel. Right. Thank you very much, Nina. At this point, we'll close off the question section. We have a comment from Suhail in the live chat on YouTube who said, "Thanks for answering my question. Great presentation as well."
Thank you so much.
I wanted to say that out loud. Now, we'll move to the quiz at this point. So anyone interested in joining the quiz, please log into the AoT Slido screen. We've just launched the quiz as live, so we can see people joining in the fun. We'll give everyone a couple of minutes to wait for you guys to catch on, because we would like to do it in real time. So please log in, and after a minute or two, we'll begin. Also, to avoid awkward silence that I've just involuntarily created, I just wanted to say that the quiz was brought to you by Johnny, who did an amazing job, and hopefully he'll be there to comment on how he tried to trick the audience.
Oh yeah, definitely.
Did you enjoy creating it?
Yeah, it was really good fun. I actually done some stuff myself because I do planets and I don't know that much about things beyond that actually, which is kind of embarrassing. But yeah, I learned a lot and it's cool. Hopefully the questions are not too hard or too easy. We'll see, I guess.
Yep. All right. On that note, let's launch them. So we are beginning with the first one, which concerns the moons of Jupiter. When have they been first observed? And I assume, Johnny, you haven't put a timer on the questions, so it's us to judge how quickly people can respond to this question. So can you tell us a little bit why you decided to talk about moons of Jupiter?
So I really like moons. Moons are really interesting objects because they're not planets, but they have a lot of the properties of rocky planets like Mercury, but also they're just very special, especially the moons of Jupiter in sort of properties they have. So Io, which is on the left there, it's very volcanic. Europa has subsurface ocean beneath the surface, we think. And I just think they're beautiful to look at as well.
Right. Did you look at the moons of Jupiter by yourself?
I have. It was, I think it was one of the first things that I saw through like a small telescope. And like the white dots that you see there, I got this image specifically because that's kind of the thing that you can see if you look through a telescope or some very powerful binoculars. It appears as a bright white dot and these 4 other ones next to it. Although Jupiter does have many, many more moons than that, these are just the biggest ones, so they reflect the most light.
Cool. Great. Great to see. So for anyone interested in looking at Jupiter, as you've said, Johnny, it's enough to have powerful binoculars to see what we're showing in the image, correct?
Yes. Not the other pictures around the outside. You need NASA grants to see those, I think.
Yep. All right. Since I've seen that the numbers have reached a substantial number of 7, let me reveal what the answer is. Oh, so wow! Almost unanimously, we've had people respond to the question saying it was 1610, and yes, indeed. You are correct. Well done, audience.
Oh, we have some knowledgeable viewers. Yeah.
Well done. And so Yeah, that was tricky because you've pointed towards particular centuries. Thank you very much, Johnny. But for those of us who remember who discovered the moons of Jupiter, who was Galileo Galilei, then I guess a little bit of a history lesson or a quick Wikipedia Google search could tell you which century he lived. And yeah, let's move on to the next question then. Thanks a lot for your personal input, Johnny. We've got the Crab Nebula. That might be a bit more tricky. So this is by far, I think, one of the most popular astronomy pictures out there, isn't it?
Yeah, definitely. It was definitely one of the things that got me involved in astronomy when I was a kid. And that is one of the reasons that's the way I got on to do my undergrad and now doing a PhD. It is kind of pretty pictures. But they are there. But it's amazing to me that this is just what we see. I believe this is slightly a false color image, but the Crab Nebula does emit in the optical. So yeah, it's not too far away.
Yeah, it is. There is a little bit of an artistic touch to make it pop more.
Yeah,
that's
definitely.
for sure.
Yeah.
And I believe it's a composite image too, because this haze that we see, I believe this is the X-ray haze. Is that correct? I might be wrong though, because I can't remember what this image particular is. But yeah, but this is true. This is something in principle, if we had good enough telescopes, we could observe, not in these splendid colors, but
no.
Yeah, so that's
maybe you'd be able to see the features and things like that. I think you're right. The haze in the middle is it's a composite image, but it's still beautiful nonetheless, I think.
Right. So how about we reveal the answers? All right. So we've got 50-50. Half of you guys said it's 11th century. Half of you said it's 18th century. And both are correct. So well done to everyone. To everyone who responded. Actually, it might be just the case that 100% of you answered correctly. No, I don't know how Slido counts votes because this is a multiple choice question.
Yeah,
I should do my homework on that one.
Yeah, so there's two correct answers because it was sort of discovered twice. So what we think of today as the Crab Nebula was actually discovered in the 18th century. First of all by John Bevis and then also independently by Charles Messier, I think 20 years later or so. But the actual supernova that led to the formation of this incredible nebula was observed and recorded by Chinese astronomers in the 11th century. So it's up to you if you decide when it was properly discovered, but that's why both are correct, I'd say.
Thanks. So we tried to trick the audience, didn't happen. We should leave less time for answers because I have a feeling some of us might be Googling this. Well, I would really Google that if I were playing now. Right. So the next question. Oh, that's by far one of my favorite images. This is a Whirlpool Galaxy M51. Sorry. Well, we of course mean the one on the left because the one on the right is the companion galaxy. Yeah. So why M51?
Again, it's just incredible to look at that. This is just how nature forms things. It's not simple physics, but gravity brings everything together in this way. And yeah, it's also just a great demonstration of a spiral galaxy, the one on the left, as you say, and then also the galaxy nucleus on the right that's its companion. I'm not sure if anyone else would be able to say if the nucleus companion is a leftover from a collision. I don't know. I'm not sure if anyone knows more about that, or if it's just been stripped.
Apologies, not very familiar with this system from a scientific standpoint. Unfortunately, these things are a bit too close for my studies. So I look at close nearby universe, but that is further away than images that Hubble can take.
Yeah.
In this resolution.
I know. I look at much smaller things, so.
Right. So let's check how people did. Oh, we've got a spread of answers. Look at that.
Ooh.
Nice. So by far, it's 1860 that's leading by People's Choice. And the answer is 1773.
Hey, we got one.
Yeah. Yep. And the name actually does reveal, if someone is familiar with the Messier catalog, the name reveals who discovered the object.
Yeah, exactly. So it's similar to the Crab Nebula, where Charles Messier was in there. He again is the one accredited with discovering and recording this. In his survey of the sky, he was actually looking for things that would distract people looking for comets, and he was making a recording of that so people could find comets better, and it gave us all these wonderful things. Yeah.
So he essentially was collecting a catalog of trash.
Yeah, he was just he was getting, all these things are annoying. Let's get those out of the way. Let's get to see the things we really want to see.
Yeah, because comets were their thing back in the day.
Yeah, they were the trend. Yeah.
Ooh, trends in astronomy. All right,
Yeah.
let's go to the next one, which is actually on the trend. Halley's Comet.
Yes.
So that's probably an object that everyone has ever. Well, it depends on the generation you're born in, I guess, but it's one of the things that you could have heard about since the day you were born, because it's such an iconic astronomical object, isn't it?
Yeah, well, it's recorded throughout history as across the world in different cultures as being seen. It appears every 75 or 76 years. And it's one of the few comets you can just see with the naked eye in the sky, and potentially twice in your lifetime if you're lucky, which is really cool. But when was it first observed? That's the question.
Yeah, so since I know the answer right now because I've been given the answer sheet, I was surprised, I must admit, because I had my answer in a different ballpark than the one that is true. So this quiz taught me a lot. I'm not going to lie.
Oh, me too. I had no idea.
Yeah, because these are, for example, Halley's Comet is so, as I've said, it became a pop culture icon, I think, in a sense, because this is one of the examples when astronomy meets daily conversation, and you've been hearing about it, but you never wonder when and how people first were able to discover it. So let's reveal the answers, and we've got a spread. Nicely done. I mean, I really like that when we've got answers that have a spread, because it actually means that nobody is looking it up on Wikipedia and are taking their best guesses. So we've got two answers that are scarily early, 3rd and 5th century, and then we've got other ones that seem more, I guess, up to date. And the real answer is, which surprised me a lot, is the 3rd century. So
yes, it's 3rd century BC. Yeah, so back to the Chinese astronomers who helped discover the Crab Nebula, that supernova. It's incredible how far it's sort of confirmed as going back. That really surprised me as well. The other dates are interesting. They're not just chosen random. So of course, 1066 is the Battle of Hastings, and it's a common theme throughout history and world cultures that Halley's Comet is sort of a sign for impending doom or a big change. I believe it was in Armenia where there was a new king in that year, and they all heralded as a sign of like great things to come. 451 is the defeat of Attila the Hun, and 1682 is roughly when it got its name that we call it today, Halley's Comet, where Halley and his friend Isaac Newton studied it together.
Yep, and I believe, if I'm not mistaken, some of the theories that link Halley to the estimated date of the birth of Christ, which is another very popular figure in modern culture. I believe, give or take a couple of years, I think Halley's Comet is also might also be, if you stretch it a little bit, might also be associated with the star above Bethlehem, right? So
yeah, well, if he appears every 75 years or so that works with the numbers there. Yeah,
exactly. Right, let's move on to the next one. Pluto, sweet Pluto. I can't get over this image. How
it's a beautiful image. Yeah,
how sharp it is compared to the first images that we might be familiar with.
Mhm.
Blurry. It's not even pixelated. It's just a blob.
It's just a blob, yeah. So this was the 2015 image taken by Voyager, which left Earth in 1970 something, I believe. So it's taken a while to get there. But yeah, if anyone's interested, go look up the sort of progression of images we've had of Pluto over the years, because this came from 2015 and it's incredible. I believe I might have just spoiled one of the answers there, but oh well.
Nope. No.
No? Okay,
I
good.
think no. You're good. I was controlling you for that, hoping I could stop you at the right place. No, but seriously, something worth at Ali. And I see that people were actually quick to respond for this one, so I'm not surprised because quite a revolutionary news past couple.
Yeah.
Especially after it's been degraded into not a planet anymore status, and all the memes appear.
Yeah. Sad times.
Yes.
How do you feel about it? Do you think it should be a planet or not?
Well, I believe it's just a matter of a label. So I understand why it's not classified as a planet, and I'm happy with it being a dwarf planet. It's sad that my children's books are wrong, but I don't mind it losing its status. We still got a mission, so it's important. So as long as we can explore it and it doesn't lose importance because it's not a planet anymore, then I'm fine. So let's check what you guys think about the discovery date. And 1930 being the discovery date by 71% of you guys. Nobody said it was 2015. Well done. And the other answers do sound plausible, actually, but the correct answer is the one that most of you chose. And the reason for Pluto being discovered so late is, well, first of all, it's far away. It's small, relatively small, and it's dim, as in because it's far away. There's very little light coming off its surface. And actually, how it was discovered, it wasn't through a direct image, correct, Johnny?
Yeah. So what it was back in the 1930s, as everyone correctly got. So what they had then was they had photographic plates, and to see the motion of a planet, you had to have two pictures side by side on the film, and then quickly switch beneath them. So you put your head in a thing and then switch between to see if there's something there, but that's in one image and not on the other. And it was a 23-year-old who'd just been employed at the observatory in Arizona, who discovered this after about a year of work, just flicking between images, basically out there. But it's very cool. 1840 was the discovery of Neptune. As one of the other answers. Nice. And then 1750 I put just because it looked nice.
Great. We like numbers that look for astronomy around.
Yeah, exactly. Yeah.
So the next one, ooh, wow, that's another iconic image. Well, you've only chosen iconic images. We've got the Andromeda Galaxy, which you sadly cannot see with a naked eye. Or no, you cannot. Maybe if you're superhuman, maybe if you're Iron Man or a Superman. But you can definitely see Andromeda with binoculars. You won't see the dust lanes as we see them right now in this image, but you will for sure see the general shape, I promise you, along with its companions, actually. And I promise you, because I've seen it myself, so I can testify that this is possible. The only issue is, since it's a smudgy area of light, you really, really need a dark sky in order to observe that. And I'm not sure where such a dark spot in England can be. Do you have an idea, Johnny? Because I observed it in Poland, and we have plenty of dark sky in Poland.
So I think one of the best places for dark skies in the UK is in Cumbria. So if you go further north and go to some of like the national parks and stuff up there, just that's some of the best places. But yeah, I've always sadly lived in places where with a lot of light pollution. So I grew up in the Netherlands, so there's a population density is quite high, and now it's in London. So I've never been the luckiest with my my night skies, but I've also seen Andromeda, and it's great.
Awesome. Well, I didn't unfortunately grow up with a dark sky either, but as I've said, Poland has a lot of dark sky parks, if you will, to offer. So, pro tip, once coronavirus is over, go visit Poland to look up at the sky. And I'm not kidding.
Good tourism plug right there.
Thank you very much. All right. So let's see what the answers are. Oh, we've got a split. Look at that, everybody. I will move us a little bit upwards, which is funnily awkward when I do that. I've just moved us up. And we've got a split of 38% equally, 1414 and 1887. And 25%, it's 964. Gee, I can't read of numbers. How am I an astronomer? Now, what is the correct answer? Please tell me, Johnny.
It's 964, actually.
Whoa! Woohoo!
Yeah, so the theme of the game seems to be the earlier the better. They knew what they were doing back then. Yeah, so it was in Persia this time. We all know Persia is a great culture ahead of its time in terms of science and medicine, and this is another one for their win book, I guess.
Which is interesting, right? Because when was the first telescope? It came with Galileo Galilei, if we trust, I guess, historical evidence.
It's like what we recognize as a telescope today, I guess. But they had sort of like glassware and things that helped them back in the 10th and 11th century, I believe.
Oh yeah. So so let's just say they didn't have advanced optics, if you will.
Optics, yeah.
So that's an impressive achievement. Right, we've got two more questions to go, and they're again exciting objects. So let's move on. 51 Pegasi b. Can you explain why the choice?
Yeah, sorry. So I'm an exoplanet person, so planets outside our solar system. And this was the first confirmed exoplanet around a main sequence star. So a star that's like not necessarily like our sun, but in the same stage of its life. It hasn't gone supernova, it hasn't ballooned up to a red dwarf yet. And this was the first credited discovery of that.
Wow.
So iconic moment for me and for astronomy in general. Yeah.
Yes. And for a field that is blowing up. Well, it's been blowing up for a while, but right now I think it's going forward in its prime, especially with the Nobel Prize recognizing the discovery of a first exoplanet.
Yeah, so it's actually Didier Queloz who's here in Cambridge who discovered that, and he won the Nobel Prize for it last year. So let's see if people remember what date he discovered it and what time he won his Nobel Prize for.
Ooh, additional ties to Cambridge. Cool. We like a little bit of flavor. Yeah, these are very thoughtful questions. Thanks a lot, Johnny.
No, I really enjoyed creating them.
So
should we see how people did?
Yeah, let's see how people did. Ooh, again, a spread. All answers have been taken up. 1995 winning with 43%. Then we've got 2006 with 29%, 1984 and 1971 equally at 14%. So, drums, do we reveal the answer? Yay! Thanks. Yeah, I like those drums. Yes, 1995, everybody. Well done to those of you who remembered. So that's a fairly recent Nobel Prize announcement. So well done.
Yeah, it's very recent. So it's only 25 years ago, and that was the first one. And now we have over, I think the latest tally is over 4,200. So as you were saying earlier, it really has ballooned in the last 20 years, and it's sort of there's an exponential growth of the planets we are discovering. At the time, Didier was only a PhD student, so there's hope for us all, Asha.
Thank you. Yeah, I would like to also mention that other great discoveries, such as the discovery of pulsars by Jocelyn Bell-Burnell, also came during her PhD, right? And that's another Nobel Prize, unfortunately not awarded to Jocelyn, PhD student, but her supervisor instead. But in either case, some great discoveries come at PhD time. So as you've said, there's hope for us all.
Yeah.
Right. The final question, the cosmic microwave
Final
background.
one.
Ah!
Yes, we've heard about it in the talk today. And again, it's another iconic and beautiful image. Yeah, I don't know what else to say about it. It's the early universe. It's just, again, it's just there, waiting for us to discover it.
Yep. Also, if I remember correctly, this is the Planck image, isn't it? The one that you're showing in the photograph.
I believe so, yeah.
Okay, so yes, this is probably the best understanding of the structure, or the best, not understanding, but the best image of the structure and its variation we have to date. And Planck satellite isn't very large, is it? It looks, well, I guess it's the size of a fridge.
Yeah.
If you say.
I'd say that's probably about right. Yeah,
Yeah.
it's not. Yeah, it's not very big. Yeah, I'm not sure kind of what size Hubble is compared to that. I think it's a bit bigger. Yeah.
Oh, that's
I'm not
another
sure.
point that we always
Yeah.
think about Hubble Space Telescope as being this gigantic structure.
Yeah.
Well, in reality, it's actually quite small. Well, JWST is going to be large once it unfolds. And
that's a big one, yeah.
And that's another instrument that I believe exoplanet studies are waiting for relentlessly, just because it will provide so much information on, I believe, planet atmospheres, if I'm correct.
Yeah, so using JWST, the James Webb Telescope, we'll be able to see into planetary atmospheres like never before. I mean, Hubble's been great, but this will give us, we'll be able to see water vapor in Earth-like planets potentially. Some people have suggested, that would be a huge thing to properly confirm that. It requires a lot of data and a lot of time, but as with Hubble, hopefully JWST goes well past its expected date of finishing.
Great. So there's something to look forward to, but let's get back to cosmic microwave background and see how you guys did. And if I could only do that really smooth. Oh my God. No, sorry. Being the technical MC, I get lost. Oh, and we've got a spread of answers. So I'm moving us again. And we've got 1964, 43%, 1974, 29%, 1994, 29%. And the real answer is... And I failed again because I switched it. 1964. Oh my God, I'm killing the atmosphere. Great. So yes, well done, guys. And this is one of the famous discoveries again, because I believe people who are interested in astronomy, they will have heard about Penzias and Wilson, right? If that's the way you pronounce it, because that's the way we would pronounce it in Poland.
Yeah. So I have to admit I hadn't heard of Penzias and Wilson myself, but I blame that on being a planet person. But I have heard of the cosmic microwave background. I'm not that bad, so yeah. But yeah, they discovered it in 1964. They went out and they built a kind of funny looking telescope to someone who works in the optical like me, but it's a radio telescope, and it's pretty cool. So definitely check it out.
Yep.
But yeah.
And they also
they won the Nobel Prize for this.
Yeah. Yep, and the funny thing is, well, I always found it very funny. Maybe that's why I remembered the names, is because they mistook the original signal for, well, they thought that they did have birds that were flying into the telescope and, let's just say, disturbing the telescope with their own poo. So they thought that's actually the signal they were getting. They thought they were measuring. They were measuring the birds that were making a mess. Yeah.
But yeah, no, they got rid of the birds. There's a funny recount of it somewhere. I can't remember where. There's these two highly experienced researchers with a broom trying to get rid of some pigeons. And if that's a great way to describe research sometimes, I think.
Yep. Exactly. So at this point, I think it brings us to the closure of the quiz. And what I haven't done yesterday is I haven't shown the leaderboard. And here it is for today's quiz. Da-da-da-da-da. So number one, taking the first place in correct answers, that's Sebastian. Well done, 7 out of 8. 7 out of 8 answers. And then the second place taken by Suhail. 5 out of 8 correct answers, but with a much smaller time. So I don't know, take it if you will. Number 3 that goes to Tina for 4 out of 8 correct answers. And the hardest question that we got today was the Crab Nebula. But that's because there were 2 correct answers, I think.
Yeah, I'm not sure how Slido counts that.
Yeah.
That might be slightly my fault, sorry. But we do love a trick question at Astronomy Untapped, so if you count that as a trick question.
Yep. So at this point, I think we're ready to say goodbye. So if I could ask everyone from the AoT team who's still in the Zoom call to come join us and say bye. Let's smoothly switch. Yes, here we are. And everyone can see us now. We're in a gallery view. Great. So let's thank Nina, our great speaker for today once again. Thanks a lot for joining us, Nina. Thank you for your expertise.
Thank you for the opportunity. Okay.
And thank you everyone for joining us for the quiz and asking great questions. At this stage, we'll say goodbye and hopefully see you next month. Maybe in person, maybe virtual. Let's see how the world rolls out. Right?
Yep. Bye,
Goodbye,
everyone.
everyone.
Bye.